A chemist compares the rates of hydrolysis of 1 chloropropane and 1 bromopropane in ethanol. Which reagent in aqueous solution should be used? A. Silver chloride, B. Silver nitrate, C. Potassium chloride, or D. Potassium nitrate. One way to compare rates of hydrolysis is using the test for halide ions. So we've got chloride ions in 1 chloropropane and bromide ions in 1 bromopropane. The test for halide ions, we use silver nitrate and ethanol, and we would produce 2 different coloured precipitates. So for chloride ions, we get a white precipitate, and for bromide ions, we get a cream precipitate. Therefore, depending on how fast these 2 precipitates form, we can compare the rates of hydrolysis. Therefore, our answer is B, and that is what you need to write to get your 1 mark. How can the molecule below be described? A. Aromatic and acyclic, B. Aliphatic and unsaturated, C. Aromatic and unsaturated, or D. Acyclic and saturated. To answer this question, we need to know what each of these words mean. So start with aromatic. An aromatic compound has a benzene ring. This molecule does not have a benzene ring, so it can't be A. But in the second part of A, we're told that it's acyclic. This molecule is acyclic because it's got a cyclic structure, which I've just circled. In part B, we're told it's aliphatic and unsaturated. An aliphatic compound is a hydrocarbon chain, which this is. But if something's unsaturated, that means that it's got a carbon-carbon double bond, which this molecule doesn't, so it can't be B. In C, we're told it's aromatic and unsaturated. Well, we've already established that it's not an aromatic molecule and it's not unsaturated, so it can't be C. Therefore, we're left with D, and that's true because a saturated molecule has no carbon-carbon double bond, which this doesn't, and it's acyclic because I've circled the acyclic structure for part A. And that's what we need to write to get this mark. Complete combustion of an organic compound forms 40 centimeters cubed of carbon dioxide and 40 centimeters cubed of water vapor under the same conditions of temperature and pressure. Which molecular formula could the organic compound have? A. C3H8, B. C2H2O, C. C2H4O, or D. C2H3N. So looking at this question, we're told that 40 centimeters cubed of carbon dioxide and 40 centimeters cubed of water vapor are produced, which means they're in the same molar ratio. So when we write our equations for complete combustion, we're looking for something that has the same molar ratio of carbon dioxide to water. If we balance this first equation, we have a 3 to 4 molar ratio, which is not balanced, therefore our answer cannot be A. If we continue, we can get our same products of carbon dioxide and water, but this time they're in a different molar ratio of 2 to 1. So again, it can't be B. If we continue to C and we balance our equation producing carbon dioxide and water, we get a 2 to 2 ratio, and therefore our answer is C because that's the same. If we continue, just to check that our answer is correct, we would, in part D, produce an extra product of nitrogen dioxide. And when balancing this equation, we can see that, again, the CO2 to H2O molar ratio is not the same. Therefore, double checking that our answer is C. Which molecule is a Z isomer? A Z isomer has its highest priority groups on the same side of the carbon-carbon double bond. So if we look at A, the highest priority group on the left is CH3, and the highest priority group on the right is fluorine. And they're on opposite sides of the double bond, so it can't be A. In B, the highest priority group on the left is chlorine, and on the right is fluorine. So our answer is B, because they're on the same side. if we double check and continue, for C, the highest priority group is chlorine on the left, and it's CH3 on the right. For D, well, on the left we can't have a higher priority group because they're both the same group. So it definitely can't be D. And it also can't be C because they're on opposite sides. Double checking our answer and making sure that it's B. Writing that will get you the mark. Which type of reaction has the greatest atom economy? A. Substitution, B. Hydrolysis, C. Elimination, or D. Addition. So atom economy is calculated by the RFM of the desired product divided by the RFM of reactants. So if there's a byproduct or a second product, then the atom economy will be lower. So addition is the only one of these reactions that has 100% atom economy because there are no byproducts produced, and therefore the answer is D, which will get you all the marks for this question. 4 atoms 1 to 4 are labelled in the structure below. Which atom has a trigonal planar arrangement of bonds around it? A. Atom 1, B. Atom 2, C. Atom 3, or D. Atom 4. Anything with a trigonal planar arrangement would have 3 bonded pairs and no lone pairs. If we take atom 1 and redraw it, it's a carbon with 3 hydrogen bond pairs and then a carbon-carbon bond pair, which is 4 bond pairs, so it can't be trigonal planar, and therefore the answer is an A. If we take atom 2, it's a carbon-hydrogen bond with another carbon, well, with 2 carbon-carbon bonds and a nitrogen-carbon bond. Again, that's 4 bond pairs, so it can't be atom 2 or B. If we take number 3, it's a carbon with a double bond or carbonyl group, and that would count as 1 bond pair. And then we've got a carbon-carbon bond and a carbon-oxygen bond. So this is 3 bonded pairs, and therefore our answer is C. If we double check and do atom 4, it's a nitrogen with 2 hydrogen-nitrogen bond pairs and a nitrogen-carbon bond pair. But nitrogen would also have a lone pair, and trigonal planar arrangements don't have any lone pairs, so it can't be atom 4 or D. Therefore making our answer C, and that would get you all the marks for this question. Which molecule is a secondary amine? A secondary amine would have the general expression of a nitrogen with 2 R groups attached and a hydrogen. We can already eliminate B and C because these are amides, not amines. So then we're left with A and D. D is a tertiary amine because it's got 3 R groups attached. So then we're left with A as our answer. And we can double check this because A is the only one that has 2 R groups and a hydrogen. Therefore, our answer is A, and that's how you get the marks for this question. What is the number of chiral centres in the molecule below? A2, B3, C4, or D5? A chiral centre is a carbon atom with 4 different groups attached. So we usually use an asterisk to signify a chiral centre. And here is our first chiral centre with an NH2 group, this group here. We've got the rest of the molecule on that side, and then there's also a hydrogen attached. Our next chiral centre is here. Again, we've got 4 different groups. There's also a hydrogen there. If we move on to our next chiral centre, here, 4 different groups. Our final chiral centre is here, which has 4 groups, it can't be anywhere else in the molecule. For example, here there's 2 CH3 groups, they're the same, that can't be a chiral center. Anything with a double bond, so this carbon here, double bond, that can't be a chiral center because there's not 4 different groups attached. Therefore, our answer is 4 chiral centers, and so our answer is C for the multiple choice. That's what you need to do to answer this question. What is the molecular formula of the compound below? A, C7H10, B, C7H12, C, C7H14, or D, C7H16. So if we first start off by counting the carbons, we know that there are going to be 7, but this is just a good way to check. So each of these dots represents a carbon atom. And now I'm going to draw hydrogen. So attached to this carbon we need 4 bonds, and we've got 3 hydrogens there to make up the 4 bonds. Here we would have 1. We'd have 2 for the rest of this pentagon, and 1 there, and 3 at the top like our first 3. So if we count these up, we've got 3 here, 1, 1 there, 2, 2 and 2. That adds up to 8 plus 6, which equals 14, and therefore makes our answer C. Equal amounts of the 4 compounds are added to the same volume of water. Which compound would produce the most acidic solution? A, CH3CONH2, B, CH3COOH, C, CH3COOCH3, or D, CH3COCl. This question is asking about hydrolysis. If we undergo hydrolysis for the 4 compounds, for A, which is an amine, the general structure of an amine is a carbonyl group with an NH group and 2 R groups attached either side. When we undergo hydrolysis, we get a carboxylic acid and an amine, in this case ammonia. For B, well, it's a carboxylic acid undergoing acid hydrolysis. It's not going to get any more acidic, so there's not going to be a reaction for that. For C, we've got an ester. When we undergo hydrolysis of an ester, we get a carboxylic acid and an alcohol, and these 2 reagents are used to form an ester, so it's the reverse reaction. For D, it's an acyl chloride. The general structure of an acyl chloride is a carbonyl and a Cl C group with an R group attached. When we undergo hydrolysis of an acyl chloride, we get a carboxylic acid and hydrochloric acid. So, linking to the question, which compound is the most acidic? Well, which compound will produce the most acidic solution? For A, we've got a carboxylic acid and ammonia. A carboxylic acid is a weak acid and ammonia is a base. So this solution would not be very acidic, and so we can eliminate A. For B, well, we've just got a carboxylic acid, which is a weak acid, but it's possible that this is the most acidic solution. For C, we have a carboxylic acid and an alcohol. Carboxylic acid is a weak acid, as I've said before, and an alcohol is a very weak acid. But they are both acids, so they're more acidic than B. For C, we've got carboxylic acid and hydrochloric acid. Well, hydrochloric acid, that's a strong acid, and a carboxylic acid is a weak acid. But together they make up a more acidic solution. So we can eliminate C, and that makes our answer D. The compound below is analysed by proton NMR spectroscopy. How many peaks are observed in the proton NMR spectrum? A5, B4, C3 or D2. So whenever you're asked about spectroscopy, you need to look for lines of symmetry. This molecule has a line of symmetry, which I've just drawn, and that will reduce the number of peaks. So next you need to look for unique hydrogen environments. We've got one in the OH group, and then you've got two hydrogens there, and they will be your second peak. And then you also need to include these two hydrogens in the line of symmetry, which will produce your third peak. And then you have the same on the other side of the line of symmetry. Therefore, you have three unique environments for the hydrogens, and so three peaks will be observed in the proton NMR spectrum, and so your answer will be C. And that's what you need to write to get your marks for this question. 0.1 moles of HOOCCH2COOH are reacted with 0.1 moles of aqueous NaOH. How many molecules of water are formed? A. 6.02 times 10 to the 22. B. 3.01 times 10 to the 22. C. 6.02 times 10 to the 23. Or D. 3.01 times 10 to the 23. So to work out the number of molecules, you need to take the number of moles and multiply by Avogadro's number, which is 6.023 times 10 to the 23. So as it's a 1-to-1 molar ratio, we can multiply 0.1 moles by Avogadro's constant, and that equals 6.023 times 10 to the 22. So if we were to round this, we would get A as our answer, and therefore that's what we put as our answer for this multiple choice question to get our mark. Which reagent should be used to prepare CH3CH2CO NHCH3? A. CH3CH2COCl plus CH3NH2. B. CH3CH2CONH2 plus CH3Br. C. CH3CH2COONA plus CH3NH2. D. CH3CH2COCH3 plus NH3. So for this question we need to understand what we're trying to prepare. This compound is what's known as a secondary amide. If we draw it out, it would look like this, and I will label the secondary amide group. It's our C double bond oxygen and NH group that makes a secondary amide. Next, we need to know what each of our reagents are. So starting at A, our COCl group, that's what's called an acyl chloride group, and will look like what I've drawn above, with a carbonyl group and then a CCl group. Then we're reacting this with an amine. An amine is an R group attached to an NH. This is a primary amine because we've got two hydrogens. We could also have another R group there, and that would make it a secondary amine, but that's not what we're reacting in this case, so we can leave our hydrogen. So this question, we need to know our OCR reaction map. So if we look at the reaction for an acyl chloride reacting with a primary amine on our OCR reaction map, here's our acyl chloride reacting with a primary amine would make our secondary amide, which is what we want. This reaction map is something that you should learn off by heart because you won't get it in the exam, but it's got all the reactions you need to know for aliphatic compounds. There's a separate one for aromatic compounds. Both are essential that you learn. So, we've established that this will produce a secondary amide. So, A is a very possible answer. If we just check the others aren't correct, for B, we've got an amide group, and we've got a haloalkane. A haloalkane is any alkane group with a halogen attached, so bromine, iodine, chlorine, fluorine, etc., any of the halogens. So looking at our reaction map for an amide reacting with a haloalkane, well, there's no reactions here for our amides. Haloalkanes, and they don't react with amides. So B is not our answer. For C, we have a carboxylate salt. The COONA is a carboxylate salt and will look a bit like this, with an O minus Na plus as one of the groups attached to the carbon, and then a carbonyl group. Then we're reacting it with a primary amine. It's the same primary amine we were reacting with in A. So if we look at our reaction map, carboxylate salt is here, and it does not react with a primary amine or anything. So our answer is not C. For D, we have a ketone here. The COCH3 group is a ketone and will look like this with two separate R groups attached. And then we're reacting with a primary amine or ammonia. So if we look at our reaction map, ketone is over here. Does it react with a primary amine? No, the amine is separate over here and will not react with a ketone to produce anything, so it can't be D. Therefore, our answer for this question is A. Ethane reacts with chlorine by radical substitution to form chloroethane. Which radical or radicals is or are present in the mechanism? 1. A hydrogen radical. 2. A chlorine radical. 3. An ethane radical. A. 1, 2 and 3. B. Only 1 and 2. C. Only 2 and 3. Or D. Only 1. For this question, it will help to draw out the mechanism. So we start by forming chlorine radicals, and that's done under UV light. A chlorine radical would react with ethane to produce an ethane radical and hydrochloric acid. This ethane radical would then react with chlorine to produce chloroethane and a chlorine radical. So if we look at our options, we've got an ethane radical and a chlorine radical, 2 and 3. Therefore, our answer is C. And that's what you need to write to get this mark. Which compound or compounds is or are structural isomers of C6H12O2? 1. Hexanoic acid. 2. Ethyl butanoate. 3. Propyl propanoate. Our options are A. 1, 2 and 3. B. Only 1 and 2. C. Only 2 and 3. Or D. Only 1. So a structural isomer would have the same molecular formula. We've been given our molecular formula, C6H12O2, but it would have a different structure. So what we're looking for is a compound that has 6 carbons, 12 hydrogens, and 2 oxygens. Hexanoic acid is what I'm drawing right now. I've drawn the carboxylic acid functional group at the end because there's no number in the molecule, and also carboxylic acid groups cannot go in the middle of the molecule. So we've got in this structure or compound 6 carbons, 12 hydrogens and 2 oxygens. So 1 is definitely a structural isomer of C6H12O2, so we can eliminate C from the multiple choice answers. 2-ethyl butanoate is an ester. This is the ester functional group, which I've just circled. And again, we're looking for something that has 6 carbons, 12 hydrogens, and 2 oxygens. The ester group alone has 2 oxygens, and the rest of the molecule we've got 6 carbons and 12 hydrogens. So 2 is another compound that's a structural isomer of C6H12O2. So we can eliminate D because it's not going to be only 1. Finally, propyl propanoate. It's another ester, and again we've got our 2 oxygens in the ester group itself. In the rest of the molecule, like ethyl butanoate, we can see we've got 6 carbons and 12 hydrogens, so making compound 3, propyl propanoate, a structural isomer of C6H12O2. Therefore, our answer is A. And by writing this, we get all the marks for this question. This question is about unsaturated hydrocarbons. Part A says that compound A and compound B are isomers. Compound A and compound B are shown below. Compound A has a lower melting point than compound B. Suggest why. Compound A is a branched chain hydrocarbon, and that's important with its melting point because it means it has fewer points of contact across the molecule, whereas compound B is straight chain, so has more points of contact. These fewer points of contact mean that compound A has fewer or weaker London forces of attraction. It's important we say London forces and not van der Waals because OCR do not accept that. And these weaker London forces will require less energy to overcome, hence compound A has a lower melting point. We get a mark for saying fewer points of contact or branch chain in this question, a mark for saying weaker London forces and require less energy to overcome. B. Compound C, CH3, CH2, CH, CH, CH2, CH2OH exists as cis and trans stereoisomers. In part 1, we're asked to name compound C. For any question where you're asked to name a compound, it's really useful to draw out the compound. So here I'm going to draw it skeletally with a 6-carbon backbone. Now we need to add the double bond and OH group. When drawing the compound, it's not crucial where you draw the double bond and OH as long as it's on the respective carbons. So if we went from left to right and we counted the double bonds on carbon number 3 from the left, 1, 2, 3 would make our double bond here, and the OH would go on the rightmost carbon. However, when naming this compound, we need to number the carbons slightly differently. We would number the rightmost carbon number 1 because that's where the OH group is. And then we would number 2, 3, 4, 5, 6 down the chain. Therefore, when naming the compound, it would be hex because it's a 6-carbon chain, 3 because that's where the double bond is, and N because it's a double bond, we need to show that in the name. 1, ol, because the OH group is on carbon number 1. In part 2, we're asked to define the term stereoisomers. Stereoisomers have the same structural formula, however, they have a different spatial arrangement of atoms. This is a definition that you need to know because it comes up a lot in OCR exams. So for each of these questions, you get a mark for part 1 for writing the full name, and you get the mark in part 2 for writing same structural formula and different spatial arrangement. That gets you the whole mark. You need to have both parts for part 2. Part C. Carbon-carbon double bond group in an alkene contains a pi bond. Complete the diagram below to show how p orbitals are involved in the formation of a pi bond. So p orbitals have a dumbbell shape, as I'm drawing right now on the carbon-carbon double bond we've been given. it's important that we label these p orbitals so then we link back to the question. A pi bond is a sideways overlap of p orbitals. So when drawing a pi bond, we can imagine these p orbitals overlapping sideways, and then we can label these as pi bonds. This will both the p orbitals in dumbbell shapes and labelled, and the pi bonds labelled will get you this mark. Part 3, we're asked to draw the structures of the cis and trans stereoisomers of compound C. I've redrawn compound C in purple above. Cis and trans stereoisomers mean that the hydrogens around the carbon-carbon double bond are in different positions. So for both of these cis and trans isomers, we can start by drawing the carbon-carbon double bond. For a cis isomer, the hydrogens are on the same side. That means the other groups will also be on the same side, but it's more about where the hydrogens are. So if we draw out the remaining groups from this compound, it's also useful for the left group, top left, that we've written C2H because the carbon bonds to the carbon, not the hydrogen. And then for a trans stereoisomer, the hydrogens will be on opposite sides, a bit like EZ isomerism, but instead of looking at the highest priority group, we're looking for hydrogens. For this question, you get a mark for each correct structure. So 1 mark for your cis isomer being correct, and 1 for your trans isomer being correct. Part D. Compound D shown below reacts with hydrogen bromide by electrophilic addition. A mixture of 2 organic compounds E and F are formed. Part 1, we're asked to suggest how a hydrogen bromide molecule can act as an electrophile. For this question, we need to know what an electrophile means. An electrophile is an electron pair acceptor. So when asked to suggest how something acts as an electrophile, we can simply write that HBr accepts a pair of electrons, which is kind of rewording this definition of an electrophile, which is a useful skill in any question like this. So writing this accepts a pair of electrons will get you the mark for this question. In part 2, we're asked to draw the structures of the 2 organic compounds E and F. I've redrawn compound D so we don't need to refer back in this question. This question was asking about an electrophilic addition mechanism. In an electrophilic addition mechanism, an alkene, such as compound D, turns into an alkane. That means that the carbon-carbon double bond will turn into a carbon-carbon single bond. We can then draw compounds E and F, or at least begin to draw them, by drawing the rest of compound D, but instead of having that carbon-carbon double bond, we have a carbon-carbon single bond. Now, carbon has to have 4 bonds, and so far, the 2 carbon-carbon double bond carbons don't have 4 bonds. Therefore, we are missing 2 things. If we look back, we know that we're reacting compound D with hydrogen bromide. Therefore, that's what we need to add to compounds E and F. It doesn't matter which side we put them on because we're not asked in this question about a major or a minor product. So, we can start by just adding a hydrogen and a bromine to each of the sides, but making sure they're opposite for E and F. In this question, you get a mark for drawing compound E correctly and compound F correctly. It doesn't matter which way round you draw them though, as long as they're both correct. In part 3, we're asked to outline the mechanism of the reaction between compound D and hydrogen bromide to form either compound E or compound F. We're asked to include curly arrows and relevant dipoles. I've redrawn compound D, so we don't need to refer back, but we need to redraw it anyway as one of our reactants in this mechanism. This is an electrophilic addition mechanism. We've been told this in an earlier stage of the question, but it's important that we know this so that you can refer back and learn it as a mechanism that you can then apply to different situations, as it does crop up a lot in OCR exams. We then need to draw hydrogen bromide, our second reactant. Now this double bond will induce a negative dipole on the bromine and a positive dipole on the hydrogen. There will then be a curly arrow from this hydrogen-bromine bond and a curly arrow from the carbon-carbon double bond to the hydrogen. We will get a mark for doing this in the mark scheme, but this will lead to the formation of an intermediate. So compound E and compound F are both alkanes, so our intermediate needs to show this, and it will be an alkane. The hydrogen can bond to either of the carbons and the carbon-carbon double bond. Here I've chosen to bond the hydrogen to the rightmost carbon. We then finish this intermediate by adding our CH3 groups. We then would have a positive charge where our bromine needs to attach to. It's positive because the bromine is left with a negative charge. We then need to draw a curly arrow from the centre of the lone pair on the bromine. It's important it's from the centre because examiners can be pretty picky for your curly arrows. And then finally, we need to draw our product because we haven't yet shown that either compound E or compound F is produced. So in our last stage, we need to write our product, including our carbon-bromine bond, which is formed in the intermediate stage. For this question, you get 2 marks for your first stage with the 2 curly arrows and the dipoles, and then a mark for your intermediate and curly arrow. In part 4, we're asked which of E or F is the major organic product. We're asked to explain our answer. A major organic product will have the most stable carbocation intermediate. So looking at compound E and compound F, which I've redrawn skeletally, just because it makes this explanation slightly clearer. For compound E, it's a secondary carbocation intermediate because there are 2 R groups attached, because this would have had the positive charge in the intermediate stage of the mechanism. For compound F, it's a tertiary carbocation intermediate because we have 1, 2, 3 R groups attached where there would have been a positive charge in the mechanism. Therefore, our major organic product is compound F, and it's because it has the most stable carbocation intermediate. Now, this is a definition that you can be asked in just the mechanism stage, and it usually comes up whenever you're asked about electrophilic additions. It's really useful to know this. So writing compound F or naming compound F or E, depending on which way you've written it, and saying that it's the most stable carbocation intermediate together will get you this mark for this question. In part E, we're told that myrcene C10H16 is a naturally occurring hydrocarbon containing more than one carbon-carbon double bond. In part 1, we're told that the reaction of 204 milligrams of myrcene with hydrogen gas produces a saturated alkane. We're asked to calculate the volume of hydrogen gas in centimetres cubed and measured at RTP needed for this reaction. We're asked to show our working. So anything RTP and volume of gas, we can use the formula volume over mole-vol, which in this case is 24,000 because we want centimetres, will equal the moles of hydrogen gas in the context of this question. So first we need to work out the number of moles of myrcene, and we can do that by taking the mass, converting it to grams by timesing it by, or dividing it by 1,000 times by 10 to the negative 3. Mass over RFM. RFM of myrcene is 10 times 12. RFM means relative formula mass, plus 16. And that will equal 1.5 times 10 to the negative 3 moles. Now we need to look at the molar ratio. We've got 1, 2, 3 double bonds in myrcene, so we need to multiply 1.5 times 10 to the negative 3 by 3, and then multiply this by 24,000, and that will give us 108 centimeters cubed of hydrogen gas. If we then write on the answer line 108, that'll get us our mark for this question. We get a mark for writing the number of moles of myrcene, or calculating the number of moles of myrcene, and then a second mark for working out the volume of hydrogen gas. You would get 1 mark for error carried forward if you don't times by 3. But it's important we times by 3 and look at the myrcene molecule, because you would have a 1:3 mole ratio. In part 2, we're told that a beta-carotene is a naturally occurring unsaturated hydrocarbon found in carrots. A beta-carotene molecule contains 40 carbon atoms, has 2 rings and a branched chain. 0.02 moles of beta-carotene reacts with 5.28 decimeters cubed of hydrogen gas to form a saturated hydrocarbon. Using molecular formulae, we're asked to construct a balanced equation for this reaction and include relevant calculations and reasoning. We can start by working out the moles of hydrogen gas in this question, because we're told the decimeters cubed of hydrogen gas. Therefore, we can use the equation of volume over mole vol, in this case 24, because it's decimeters cubed, to get moles. So plugging in the numbers, we get 5.28 over 24 equals 0.22 moles of hydrogen gas. We can then work out the molar ratio by dividing 0.22 by 0.02, and we get 11. This means we've got 11 double bonds in our molecule, and therefore our product would be C40H78. Using reasoning, we then work out that our reactants be the hydrogens from C40H78 minus 22, which would be H56, because we're adding 22 hydrogens to get our product of C40H78. In this question, we get a mark for working out the moles, a mark for working out the number of double bonds, a mark for working out our product, and then a mark for our equation. This question is about the chemistry of aromatic compounds. In part A, we're told that benzoic acid can be nitrated by concentrated nitric acid in the presence of concentrated sulfuric acid as a catalyst, as shown in equation 17.1. The organic product of this reaction is 3-nitrobenzoic acid. In part 1, we're asked to outline the mechanism for this nitration of benzoic acid and show how sulfuric acid behaves as a catalyst. This mechanism is known as electrophilic substitution, and the first stage of an electrophilic substitution mechanism is the formation of the electrophile. The electrophile in this case would be formed by sulfuric acid and nitric acid. Our electrophile is nitrogen dioxide, but with a positive charge, water, and sulfuric acid, but with a hydrogen removed and a negative charge. In the first stage of this mechanism, we need to react our electrophile with benzoic acid. There should be a curly arrow from the benzene ring to the electrophile, and in the intermediate we draw a sort of smiley face to show where the nitrogen group is going to end up. So here's what I call a smiley face. You would get kind of two possible routes and a positive charge in this smiley face. This is because the hydrogen from the benzene gets attracted back into the group and therefore would form 3-nitrobenzoic acid. Alongside a positive hydrogen. This positive hydrogen will react with our sulfuric acid ion to reform sulfuric acid and show that sulfuric acid acts as a catalyst because it's reformed in this mechanism. In this reaction or question, we get a mark for the curly arrow in stage 1 and the formation of the electrophile. We get 2 marks for the correct intermediate and curly arrow and a mark for the reformation of the catalyst, and that will get you 5 marks for this question. Part 2. The chemist carries out the reaction in equation 17.1 using 4.97 grams of benzoic acid. The chemist obtains 3-nitrobenzoic acid as an impure solid. The chemist purifies the solid to obtain 4.85 grams of 3-nitrobenzoic acid. Describe a method to obtain a pure sample of 3-nitrobenzoic acid from the impure solid. Determine the percentage yield and check its purity. For this question, we need to write the stages of purification. There are 4 stages of purification. First, recrystallization. We need to state recrystallization. That's a key word for this question. Secondly, dissolve solid in a minimal amount of hot solvent. The key words here are minimal amount and hot solvent. This is a level response question, so you get marks for detail. Thirdly, the third stage of purification is that you need to cool the solution and filter the solid. In this stage, cool, solution, or cool and filter are our key words to get the marks for this stage of purification. The final stage of purification is that you need to wash with cool solvent. Here, cool solvent is the key word. Then, for percentage yield, we need to work out the number of moles. We do this by using the grams of benzoic acid and 3-nitrobenzoic acid and dividing by their relative formula masses. So, for benzoic acid, 0.0407 moles of benzoic acid, and then for 3-nitrobenzoic acid, we do the same thing, take its mass of 4.85 grams and divide by its relative formula mass of 167 to get 0.0290 moles of 3-nitrobenzoic acid. Then, for percentage yield, we take the moles of 3-nitrobenzoic acid and divide them by the moles of benzoic acid. And then we multiply this by 100 to get percentage of 71.3%. To check a purity, you need to do a melting point test. A melting point test will give you a result, and to check the purity of your result, you can then compare your results to known values which you can simply search on the internet, and that will give you an indication of how pure your sample is. As this is a level response question, you get marks for detail, the correct percentage yield, and checking purity. B. A student investigates the relative ease of nitration of phenol, benzene and benzoic acid. The student finds that the conditions required for the nitration of each compound are different, as shown in Table 17.1. In Part 1, we're asked to state the trend in the relative ease of nitration of phenol, benzene and benzoic acid. Because this question is asking us to state the relative ease, we don't need to go into a lot of detail. This question requires us to say that phenol is the least reactive, and that's because it doesn't require a catalyst and is at the lowest temperature, and it's dilute nitric acid that it requires and not concentrated. But then we also need to write that benzoic acid is the most reactive, and that's because it requires a catalyst, has the highest temperature, and concentrated nitric acid is required. So by writing these two statements, we can get this mark for this question. Part 2. Apply your knowledge for bonding in arenes to explain the trend in Part B(I). For phenols, the lone pair on the oxygen is partially donated to the pi ring system. The lone pair on the oxygen comes from its OH group in the phenol. For benzoic acid, the carboxylic acid group is an electron withdrawing group, and that means that it's going to be more reactive. Then we need to link by saying that phenol has a higher electron density, and therefore it's more susceptible to electrophilic attack. We don't need to write electrophilic attack, but that's a good bit of background knowledge that you can carry on using in the exams. To get the marks for this question, we need to say the phenol has a lone pair, which is partially donated in the ring system. That statement that the carboxylic acid group is an electron withdrawing group, and we need to do the link between the phenol having a higher electron density and it being more susceptible to attack, therefore it's less reactive. Part C. A student synthesizes 3-bromophenylamine shown below, starting from nitrobenzene. Part 1. Complete the flowchart showing the structure of the intermediate and the formulae of the reagents for each stage. We're told that the first stage is bromination, therefore one of our reagents must be bromine, but we also need a halogen carrier in order for this reaction to occur. This would form an intermediate, and the intermediate would have the bromine in the third position because a nitro group has a 3,5 directing effect. Therefore, in reduction, we're going to reduce this nitro group, and the reagents we need are tin and concentrated hydrochloric acid. These are reagents that you need to know off by heart. There's a flowchart for OCR exams with all of the reagents and reactions on that you can refer back to and we can go over in future videos. But writing the reagents for the two stages and the correct intermediate, those three components will get you the marks for this question. Part 2. Another student attempts the same synthesis but carries out reduction before bromination. The student was surprised to find that 2 structural isomers of 3-bromophenylamine had been formed instead of the desired product. Explain this result and suggest the structures of the 2 isomers that formed. As I said before, a nitro group has a 3,5 directing effect, but if you carry out reduction first, you have an NH2 group, which has a 2,4 directing effect, and therefore the bromines will be in different locations around the benzene ring. So our first structure will have the bromine in the second position around the benzene ring, and our second structure will have bromine in the 4th position around the benzene ring, which are different to our product. For this question, the explanation of saying that NH2 groups have a 2,4 directing effect gets you the first mark, and each structure being correct will get you a mark for this question. This question is about organic compounds containing nitrogen. Part A. Sodium cyanide can be reacted with many organic compounds to increase the length of a carbon chain. Part 1. 1-chloropropane reacts with ethanolic sodium cyanide by nucleophilic substitution. We're asked to outline the mechanism for this reaction, include curly arrows, relevant dipoles, and the structure of the organic product. For any mechanism, we need to start by drawing our reagents. Nucleophilic substitution is one of the 5 mechanisms that you need to know because it can come up in any organic exam and potentially a unified exam. Here I've drawn my reagents. We get a mark for the curly arrow from the cyanide, which acts as our nucleophile to the carbon, and that's because of the induced dipoles. There's also a curly arrow from the carbon-chlorine bond to the chlorine. Then, in the final stage of the mechanism, we need to show that the length of the carbon chain has been extended, and this is because the cyanide bonds instead of the chlorine, so we get a chlorine ion at the end. So, to clarify, we get a mark for our curly arrows, a mark for the dipoles, and a mark for including the chloride ion in the final stage of the mechanism. Part 2. Compound G is used to synthesize compounds H and I, as shown in the flowchart below. Complete the flowchart showing the structure of compound G and the formulae of the reagents for reaction 2 and 3. If we start by trying to find compound G, reaction 1 is a nucleophilic addition reaction. A nucleophilic addition reaction is between a carbonyl group and will either form an alcohol or a hydroxynitrile. In this case, we formed a hydroxynitrile. So our carbonyl group, which is a C double bond O, will be an aldehyde, and it will have a hydrogen as its R group because the CN, without it, there's only one carbon in the molecule. Then, looking at reaction 2, it's a reduction reaction, which means we need a hydrogen, or hydrogen gas, and a nickel catalyst. Then, reaction 3, the cyanide group has turned into a carboxylic acid. For this to occur, we need an aqueous acid, for example, hydrochloric acid. But sulfuric acid would also be accepted, as long as the formula is correct. For this question, you get a mark for compound G, the reagents for reaction 2, and the reagents for reaction 3. Part 3. Compound H reacts with dilute hydrochloric acid to form a salt. Explain why compound H can react with dilute hydrochloric acid and suggest a structure for the salt formed. Well, compound H, which I've drawn so we don't need to refer back, has a nitrogen. And nitrogen would have a lone pair. So the nitrogen lone pair will accept a proton. We can write the proton as an H+, and that will help with our structure because the salt will have an NH3+ group, and then to make sure that it's a salt we need to balance the charge, and we can do this. With hydrochloric acid we've got the chloride ion, and there together would make our salt. For this question we get a mark for our explanation of the nitrogen lone pair accepts a proton, and the correct structure for the salt for this question. Part 4. Compound I is the monomer of the biodegradable polymer J. Draw 2 repeat units of polymer J and suggest a reason why it's biodegradable. In compound I, which I've drawn above, we've got a carboxylic acid group and an alcohol group. So if I just show these, our carboxylic acid group is here and our alcohol group is there. Therefore, in our polymer, we would have an ester link. Here I'm just drawing what an ester link looks like. Then if we work backwards, the single O here, that comes from the alcohol group, and so will be attached to a carbon with 2 hydrogens. And the carbonyl group, or carbon double bond oxygen, would also be attached to a carbon with 2 hydrogens. Then if we complete this polymer, we only need to draw 2 repeat units, like so. Now, you don't have to write brackets and a N for this question, but it's really useful too, because a lot of questions, they can have it in the mark scheme, some don't. So to be on the safe side, it's useful to draw your brackets and an N, because you won't lose marks if you include them, but you could if the mark scheme says to. If it doesn't, it's not going to affect anything, it just says to ignore them. So I'd recommend always including them when drawing polymers. Suggestion why it's biodegradable: an ester link can be hydrolyzed, and it can be hydrolyzed in acid or base hydrolysis. So for this question, you get 2 marks for the polymer and 1 mark for saying that it can be hydrolyzed. B. The repeat unit of nylon 6,6 is shown below. Part 1. Draw the structures of the 2 monomers that can be used to form nylon 6,6. In nylon 6,6, we've got an amide group, or link, as it's known in polymers, which means we're going to use a carboxylic acid and an amine. It's a condensation polymer, so that means that we're a byproduct of this process, we would form water. This is not useful in the question, but it's good to have in the back of your head when checking. So, our carboxylic acid, well, we can already see where it's going to come from based on the polymer. It's going to come from this section of the molecule. And so we can just draw the remaining parts of the polymer, but as carboxylic acid groups. Just double checking we've got the right number of carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Then, drawing our second monomer, we would have our amine, so nitrogen with 2 hydrogens, and then our carbon backbone, and again our amine. Double checking our carbon backbone is the same length, because this is where a lot of people would stumble up in the exam. 6 carbons, 1, 2, 3, 4, 5, 6 carbons. These numbers aren't critical in the exam, so we can now erase them. For this question, we get a mark for each monomer, and that will get you 2 marks for this question. Part 2. A sample of nylon 6,6 has a relative molecular mass of 21,500. Estimate the number of repeat units in the sample. Give your answer as a whole number. Well, we can first work out the relative formula mass of our nylon 6,6 sample that we were given in the question or part above. So relative molecular mass, that would be counting the number of carbons and timesing it by its relative molecular mass. There are 12 carbons in this molecule. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, plus 2 oxygens and 2 nitrogens. And then we need to count the number of hydrogens. And when we count them, there are 22. This gives us a relative molecular mass of 226. So we can take our 21,500, divide it by 226, which gives us 95.1. But in the question, we're told we want the answer as a whole number. And so the number of repeat units is 95. So writing 95, that gets you the marks for this question. This question is about alcohols. A. Construct an equation for the complete combustion of an unsaturated alcohol with 5 carbon atoms. The general expression for an unsaturated alcohol is CnH2nO. Therefore, if we had 5 carbon atoms, we would write C5H10O in our equation. Combustion means we're going to react with oxygen, and we're going to produce carbon dioxide, not carbon monoxide, because it's complete combustion. And then we're also going to get water, or water vapour. We then need to balance this equation. 7 oxygens, 5 carbon dioxides, and 5 water vapour. So, to get this mark for this question, we need to have the complete and correct equation for part A. Part B. Many alcohols, including ethanol, are soluble in water. I. Explain with the aid of a diagram why ethanol is soluble in water. Include relevant dipoles and lone pairs. So this question is asking about intermolecular forces. So if we were to draw out ethanol, there is a specific type of intermolecular force that we're going to show in this diagram, and it's called hydrogen bonding. Here I've just drawn ethanol. We need to include the dipoles, a negative dipole on the oxygen, positive on the hydrogen. There is then a hydrogen bond between this oxygen in the alcohol group on ethanol to water. You need to make sure that the hydrogen bond is going from the centre of the lone pair on the oxygen, and then you need to draw the lone pairs on the water, making sure you've got a positive dipole on the hydrogen, negative on the oxygen, and positive on the hydrogen, because it induces it across the water and the oxygen groups. Then, to get your second mark, you need to label the hydrogen bond. It's really important that you do this, otherwise the diagram doesn't really make much sense to an examiner. So to get this mark, or these 2 marks, you need to first draw the correct diagram, making sure your hydrogen bond is from the centre of the lone pair on the OH group, or the O in the OH group, and label your hydrogen bond. If you wanted to, you could also write a little sentence just saying that ethanol can hydrogen bond and therefore is soluble in water, but that won't get you any marks, but it's a good piece of information to have in the back of your head when doing a question like this. Part 2. The solubility of hexane 1-ol and hexane 1,6-diol in water is shown below in table 19.1. Explain the difference in solubility of hexane 1-ol and hexane 1,6-diol. As said before in the earlier parts of this question, solubility in water is because of hydrogen bonding. Hexane 1,6-diol, well, the di in diol means that it's got 2 OH groups, so has more OH groups. That means that it can form more hydrogen bonds. But we need to link to the question, and we're saying the solubility in water, so forms more hydrogen bonds with water, making sure that we're linking to the question, fully answering. So to get this mark for this question, you need to say that hexane 1,6-diol has more OH groups, so more hydrogen bonds with water. Both of these statements will get you the mark for this question, making sure we have both. C. Alcohols are important in organic synthesis and can be formed by the reduction of carbonyl compounds. Part 1. Complete the flowchart by filling in each box. When completing a flowchart, it's important to link back to our mechanisms. If we start with compound K reacting with NaBr and sulfuric acid, well, this is nucleophilic substitution. In nucleophilic substitution with an alcohol, you would turn into a haloalkane, so the alcohol will be replaced by a Br group. In reduction, it's a carbonyl compound getting reduced, so it's nucleophilic addition. The reagents for nucleophilic addition are NaBH4, also LiBH4, both are acceptable. a carbonyl compound, well, carbonyl group is a C double bond O group, so we need to make sure we show that in our compound. Then, for compound K reacting with an acid, catalyst and heat, that's an elimination reaction, where the OH group is replaced with an alkene group. So the alkene group could go either side of the alcohol group on this cyclic structure, and that makes our two structural isomers. To get the 5 marks for this question, you get a mark for each structure and then a mark for the correct reagents of reduction. Part 2. What is the name of compound K? Well, compound K, if we ignored this methyl group for a minute, that would be cyclohexanol. But we need to include this methyl group because it's in compound K. So, like with any numbering, I've drawn out the structure, and we number from the highest priority group around the carbon chain. So the methyl group that I have circled, that's on carbon number 3. So, in our name, we would write 3-methyl cyclohexanol. And that's how you get the mark for this question. D. Butan-1-ol can be oxidized to form 2 different organic products, depending on the reaction conditions used. Describe both oxidation reactions of butan-1-ol. For each reaction, include the structure of the organic product, a balanced equation, the essential reaction conditions. In your equations, you may use O to represent the oxidizing agent. So, oxidization for a primary alcohol, which butan-1-ol is, there are 2 different routes that we could take. If we draw butan-1-ol out, well, that's butan-1-ol drawn skeletally, and then we add our oxidizing agent. If we distill butan-1-ol, we get an aldehyde. An aldehyde is a carbonyl group which has a general formula of C-double-bond-OH with an R group. If we continue to oxidize butan-1-ol, so having 2 oxidizing agents, and this time we reflux, this is a second condition, we would this time get what's called a carboxylic acid. The general formula of a carboxylic acid is an R group C-double-bond-O-OH. So, to get the 5 marks for this question, we need to have the correct equation, and then you get a mark together for distillation and reflux. So you get 2 marks for your equation and product for both stages, and then 1 mark for the both reaction conditions being correct. A chemist analyses a naturally occurring aromatic compound. Part A. The percentage composition and mass spectrum of the compound are shown below. Percentage composition by mass: C 70.58%, H 5.92%, O 23.50%. Determine the molecular formula of the compound and show your working. Firstly, what we need to do when answering this question is work out the empirical formula of the compound. We do this by taking the percentage compositions by mass of C, H and O. So for carbon, we have 70.58% and we divide it by the relative formula mass of carbon, hydrogen or oxygen. So for carbon, that's dividing it by 12. That gives us 5.88. Then for hydrogen, we have 5.92 divided by 1, and that gives us 5.92. For oxygen, we have 23.50 divided by 16 gives us 1.46875. The next step in working out empirical formula is divide by the smallest value. This would be 1.46875. So dividing oxygen by that gives us 1. Dividing hydrogen by 1.46875 gives us 4. And dividing carbon by 1.46875 also gives us 4. So that makes the empirical formula C4H4O. We then look at the mass spectrum. The rightmost peak, or furthest to the right peak, that gives us the relative formula mass of the entire compound. So if we read off this peak here, that's at 136. So that means that the relative formula mass of the entire compound is 136. So if we look at the relative formula mass of the compound we've worked out, that would be 12 times 4 plus 4 plus 16, which gives us 68. So then we need to multiply by 2 to get 136, because 136 is 68 multiplied by 2. So that would make the whole relative formula mass of the compound correct. So that makes our molecular formula C8H8O2. In this question, you get a mark for working out the empirical formula, a mark for multiplying or reading from the mass spectrum, and a mark for getting your molecular formula correct. B. Qualitative tests are carried out on the aromatic compound. The results are shown below. Determine the functional groups in the compound and explain your reasoning. If we start on the right, Tollens reagent is a test for an aldehyde. Here I'm just drawing the general structure of an aldehyde. If there was an aldehyde present, Tollens reagent would react with the aldehyde group and form a silver mirror. But there's no observable change, so there's no aldehyde group. 2,4-DMP is a test for a carbonyl group, and the positive test for a carbonyl group is an orange precipitate, which the person has observed. Therefore, there is a carbonyl group. Sodium carbonate is a test for carboxylic acid. Here I'm drawing the general structure of a carboxylic acid. If there was a carboxylic acid present, the observation would be an effervescing or fizzing. But there's no observable change, so there's no carboxylic acid. The acidity of pH 5, well, that's pretty weak, so it's a weak acid. Therefore, our functional groups are a ketone because there is a carbonyl group, but no carboxylic acid or aldehyde. So it's got to be a ketone. So ketone. And then a phenol. Phenol because it's a weak acid, and also linking to the question, well, it says that it's an aromatic compound, and phenols are aromatic compounds. So to get this 3 marks for this question, you need to have the correct functional groups, ketone and phenol, and your explanation needs to suggest that there's no carboxylic acid, no aldehyde group, so it must be a ketone, and that the compound is a weak acid, so the phenol group is your other functional group, and that's how you get 3 marks. C. The carbon-13 NMR spectrum of the compound is shown below. Using the spectrum and the results from A and B, determine the structure of the compound and explain your reasoning. If we start on the right of the spectra, this peak for the rightmost side, if we compare the values to the data sheet, that's a carbon-carbon bond peak. So in our reasoning, peak between, we write between because for spectra we say a range, you won't have exact values, between 20 and 30 ppm is a carbon-carbon peak. Then, moving left, we've got these 4 peaks in the middle of the spectrum? Well, they show or signify an aromatic. So, peaks between, again stating a range, this time 110 and 160 ppm are for aromatic compound, which we know is going to be a phenol. Finally, our peak on the leftmost side, so peak between 190 and 200 ppm is for a carbonyl group. Then for our structure, we can start by drawing a phenol because we know that that's going to be in our compound. Here, drawn a phenol, and then we need to draw our ketone. Here, I've drawn our ketone. Now we need to do a bit of checking. First, we need to check that we've got 6 carbon environments. So if we number them, 1, 2, now here on the benzene ring, they would be symmetrical. So 1, 2, 3, 4 around because they're the same environments if we drew a line of symmetry. Then we've got 5, 6. If we compare the 5 and 6, well, 5 would be for our carbonyl and 6 would be for our carbon-carbon bond. Then if we check the molecular formula, we can check we've got 1 carbon, 2, 3, 4, 5, 6, 7, 8. So we've got 8 carbons. Have we got 2 oxygens? Well, that's easy to check. We've definitely got that. Then for the hydrogens, bit more thinking. We've got 1 there. We would have 1 hydrogen on each benzene point or each phenol point. And then we would have 3 towards the end because a carbon at the end would have to have 4 bonds. So we would have 3 hydrogens. So if we count these all up, 1, 2, 3, 4, 5, 6, 7, 8. We have 8 hydrogens. For this question, you get 2 marks for your reasoning and you get 1 mark for the correct structure.